So for the second session today, we're still carrying on with relational data, and what we're looking at for this part will be more on how we can use that information and link it together in different ways, and explore what sorts of relationships between tables can happen. So only a couple learning outcomes for this second session. To sort of think about why we might want to aggregate data to a higher or lower level. Also explain the differences between the different types of data merging, binding, and joining that we can do through these different relationships between the tables. So just to quickly go over it again. So we have established what relational data is, that we have this stock of multiple linked data sets, and these can be linked using primary and foreign keys that uniquely identify each record or each unit within a table. And we can split these based on levels of a hierarchy or potentially time points. And we can store these in separate database tables or across multiple sheets of an Excel workbook or even individual data files. So one thing we want to do a lot of the time when we have relational data is that we want to perform some sort of data aggregation. It's a very common thread also when it comes to analysis, but we can also do some of this aggregation as part of the data cleaning and the data tidying and the data management. So especially if you already have a data analysis plan in mind, and if this is with whoever is doing the data cleaning and the management, which could be a very useful step, then they can, as part of their process, start making some of these aggregated variables that will be useful later down the line. So, for example, we can summarize plot size across each of our farms through that plot level table. We could total that up or make an average. And from that, we can then bring that information up to a farmer level data table to create a variable for the total plotting area. And we can do this between any two levels of our data. We don't have to just bring this up the one time. We could take the plot size, make a total and bring that up to the farmer. And then through the farmers, if we wanted, we could look at all the farmers within a village and take the average of their plotted size and bring that up another level to perhaps a village level table that we have. We could store what the average plot area for each village would be in that extra table that we have as well. We don't have to stop at just jumping up one level. We can jump two or even more. So now we have data always readily available at the level it is required for the analysis. We don't have to create these variables and do this data merging later down the line when we want to focus on our analysis. We know we have that variable ready there and we can just use it straight away. But as well as bringing data up, we can bring data down a level. So this would be, I think, commonly when I've done it before, is if you want to aggregate data at one level by a variable that's been stored at a higher level. So this is more that you want to stay at this lower level for whatever reason. Perhaps you want to stay analyzing plot sizes. And so for one example, what you want to do is maybe look at the average plot size between male and female farmers. And now what you might not want to do is bring that data up. That could be a bit more confusing, perhaps. So instead, maybe what you do is bring that sex variable down from the farmer. So you merge this data downwards and then group the plots in that plot data by the sex and then take an average. So this is probably less common, I would say. Maybe a step more likely that you would think about later during your analysis, but the technique is the same as trying to move in the opposite direction. So whenever we're thinking about how we can start linking these tables together, something that you will want to consider is how these tables are actually related, not just in the sense of what key links to what key, but think what type of relationship it is. So we saw briefly in that YouTube video I showed at the start of the previous session, is that he noted how one row in classes can link to many rows in the enrollments table because one student can take many classes. And then similarly, one class can link to many rows in the enrollment table because, again, one class can have many students. So that was him sort of getting into this idea of how these two tables link. So you want to think about this as well, and there's a few different ways in which this happens. So there's kind of three kinds of these relationships that you can have between tables. You can have a one-to-one relationship. So this is how your keys, they only refer to one row in each data set. So this is a bit like how we have with the longitudinal data, in that each table will be about the same households, and there will only be one row per household in each table. So one farm at time X links to only one farm at time Y. There's no multiple rows within one of those data frames linking. It's always one to one and they match, and nothing else. Nothing else other than that one row will match with that row. And then to extend that, you have what's called a one-to-many relationships. This is where you have two tables, and one row in one of the data tables can link to many rows in the other. But this relationship isn't returned, that those many rows still only link to the one row in the other table. So this is sort of, you have one farm and they have many plots, but one plot won't link to many different farms. It's that one way round, one farm, many plots. And then kind of what we actually had before in that YouTube video, before the enrollments table was created, classes and students were actually a many-to-many relationship before that enrollments table was made. So with a many relationship, what you have is that identifiers can link multiple rows between both data sets. And this is because when you're thinking about just students and classes, you have the multiple students can be in multiple classes, and multiple classes can be taken by the same students. So you have many rows from both tables can link together in some way. And that's why he creates this enrollments table to simplify that linking. So an example I came up here is that you could have some external and secondary information, perhaps on average, cost or yield on a certain type of crop in one table. So you have this information about types of crops in this one table. And this could be linked to their growth on different plots in your data. But the issue there is that one plot can grow many different types of crop, but also one crop, say sorghum, many different plots could grow sorghum. So you have many plots linking to many crops and many crops linking to many plots. This is where many-to-many comes in. And then that's where, in this example, perhaps you would want that third, what's known as a join table, where you are able to simplify this information down so that you have a plot within plot level table. Just going to see if there's anything on the chat. Can you explain how to bring the female variable down on a construct? So linking tables, that's where we're getting on to, don't worry. So yeah. So now we're going to go on how we can sort of merge information, the different ways information can be merged. The specifics of merging tables in R, at least this will be within the workbook that will be after today's session. So as we had with Monday and Tuesday, the same will be available today. There'll be one that will cover this sort of information on summarizing information and then how to do different data merges within R. So the simplest form of data merging is what we call binding, although it is for particular situations. So either you have two tables and they are from the same survey / set of measurements, but they contain different sets of observations. So it could be that you have all of your data collected from one location, and you have all your data collected from another location. And they've used the same survey tool, so the basic structure of those two data sets is the same. But as they are currently stored in separate data tables, you might want to bring this together. And this is known as row binding, because you are, so this is with the top diagram, you have this first set of data and you have the second set of data. And what you want is just to simply stack one on top of the other and just bind them together by according to their rows. And in the case of row binding, that it's kind of depends on how you do it. There's a few different variables, at least when it comes, a few different functions, sorry, within R when it comes to this. Not sure about other pieces of software, but there's kind of two ways to do it. And one of them requires that these columns are named the same and that there are the same number of them. There is an alternative one, which you'll see in the workbook, that doesn't require the same number, but it does require that they have the same names when they are mutual. And if it doesn't find a match between certain columns in the two data sets, it will just leave that information as missing for where it is missing in one of those tables, but it will still do the binding. The other scenario is where you have two tables of the same set of observations, but different measurements. So this could be an example of linking data from a baseline and endline survey. Perhaps you do want it in wide format for whatever reason. You would have the two sets of data and they would contain the same observations, and you would be able to bind them instead by columns rather than rows. And this is a case where regardless of regardless of how you're doing it, that the same number of rows need to be present in both data sets. So binding is an example of merging two data sets, but the rules regarding the structure of those tables is quite strict. But moving past binding, we have something a little bit more technical, which is known as joining. And this is something you probably will use more commonly, not just in R, but whichever software you're using, you're probably going to be doing some sort of join. This is how most data merging is going to occur. This is what we would do when we are merging data that is across these different levels. So when we are bringing data down or bringing data up to these different table levels, that joining is how you would do it, because we have these identifiable keys between the two tables that we can use to match between these respective data tables. And generally, there are sort of three types of joining. We have what's known as a full join, an inner join, and what we tend to call a left or right join. Now, in all these scenarios, we have to make it clear which are your key variables that you're matching between, and sometimes not just your keys, but also any existing columns which are present and mean the same thing in both. Because sometimes if you do only specify that primary and foreign key, then sometimes if there are columns which are already present in both, then it won't merge those together as well. It will end up saying, say for example, sex was already present in both data sets, rather than leaving it as one sex column, even though it says all the same information, it creates two columns for it instead. So sometimes there is more than just the keys that need matching, but the keys are your main point of reference. So a full join. In a full join, what we are doing is basically keeping everything. Is that all of these joins, the only way in which they differ really is in terms of what information is left after you perform the join. So in a full join, the data table that you end up with, it will contain every row from both tables, whether or not there was actually a match between them. So everything is kept and nothing is lost whatsoever. So as you can see in this little diagram, which comes from the R4 Data Science book, which has been linked at the end of every presentation, and the link you can find for that on the course website. You can see that in this X table, we have observations 1, 2, and 3, but we don't have that fourth observation. And then in the Y table, we have 1, 2, and 4. We don't have any information for 3, however. So, but because we're using a full join, the table that gets presented is that we have all 4 of those observations. We have 1, 2, 3, and 4. And for 1 and 2, as there was a match, we keep the variables from X and we keep the variables from Y, and they are matched together on the same row because they are matched on the key. But for 3, while we have their X variables, because there was no match in Y, that all retains as missing. There was no information to match. And for 4, likewise, we keep its Y variables, but there's no information there to fill out for X. And this is what we would expect from a full join, is that where this information is missing, it is still kept. So this could be useful if you're merging data from 2 separate survey rounds, as the second round could include people who were not interviewed in the first, and likewise also missing people from the first round due to survey attrition. If your goal is not to lose that information for the observations who are missing at one of those 2 time points, then a full join will keep everybody. It won't lose any of those observations which don't have information from one of those survey rounds. So then next we have what's known as sort of left/right joins. This type of join will only keep all of the rows from one of the 2 data sets, regardless of the match. So the main difference between a left and right join is actually just the definition of your primary data set. So if you're using a left join, the rows are kept from the table that's specified in the function first. If you're using a right, then you keep from the table that's second. It's left keeps everything from your X, right keeps everything from your Y. And this is what you can see in the diagrams, in that we have a similar setup, in that we have to the X, we have rows 1, observations 1, 2, and 3. In Y, we have 1, 2, and 4. we don't have anything for free, but what we produce, we'll keep 1 because there is a match, and we get the X variables and the Y variables. 2, the same, we have the X and we have the Y. And now 3, that stays because we have said we want to keep everything from that left data table. So we keep it and we keep its X variables, but we don't bring any Y values because there was no match with the 3 of that other data table. And we don't keep 4 in the same way we did in that full join because there is no match there. And now basically the reverse is happening with the rights join, in that we keep 1 and 2 the same, but it's 3 that we drop rather than 4 because we've said our rights table is our main point of reference. So this is probably the type of join you would use the most when, and definitely what you might be using when you are merging data between different levels of a hierarchy, because at that point you probably have a unit of analysis which is considered your primary, whether it's the farm or the plot, and you are joining information onto that table. But it's probably likely that you are going to want to keep everything from that primary data table, because that's what matters most. You don't want to start, say if you are focusing on the plot and you want to bring some information down from the farm, you probably don't want to bring down information about farms that didn't have any plot information, because basically if you do a full join there, then you bring down information for farms that didn't have any information to give, or at least no information that is going to be useful because they didn't have any plots. Well, the alternative to these is then what we call an inner join, and this takes this filtering 1 step further. It will only keep the rows where there is a match between the 2 tables. So any row that is unmatched will just be dropped from the resulting table. So this is for when you want to create tables that will only have the full set of information. So if you really want to only focus in on the information where your data is not going to be missing, so where you have both that X and that Y. So back to the longitudinal example, this would be, you have your baseline, you have your end line, but ultimately you only want to perform analysis on those households which took part at both points. That's what an inner join will do. It'll get rid of all rows that only appear in one of the 2 tables. There are a couple other types of joins, but they're not ones that seem to come up very often, and so you'll only be very certain situations and probably mainly use it for filtering. It's neither of them are particularly ones that I've used in the past, but just for the full nature of it, we have a semi-join, which will keep observations in X where there is a match in Y, but it's not adding those variables from Y. It's basically being used to filter your X data set, just based on something from another data table, but it's not actually merging them. You're just subsetting your data. And kind of the reverse of all of these is an anti-join, which is creating a new table, but it will only keep the observations where there was no match whatsoever. Not one I've ever actually found a particular use for, but it is out there. And all of these sorts of relationships are true regardless of what you're using. So we'll also be looking at how you use these types of joins in R, but I know that SQL, for example, as a database software, uses the sort of same terminology. It is sort of general terminology for these different data join relationships.